Hey everyone, Hugh here from LeetCode. Today we're solving LeetCode 1679, max number of k-sum pairs. This is a medium difficulty problem, and it comes under arrays and hash table in the LeetCode 75 study plan. At first glance, this problem looks pretty simple. We're just finding pairs that add up to a given number. But there's an important restriction. Once a number is used in a pair, it cannot be used again. That one condition completely changes how we approach the problem. The interesting part isn't finding a pair. It's finding the maximum number of valid pairs. So let's first understand exactly what the problem is asking. We're given an integer array called nums. And we're also given another integer k. Our goal is to perform an operation as many times as possible. In one operation, we choose two numbers whose sum is exactly k. Once we use those two numbers, they are removed from the array. That means they cannot be used again. We keep repeating this process until no more valid pairs can be formed. Finally, we return the maximum number of operations we were able to perform. Notice something important. The question isn't asking us to return the pairs. It only wants the maximum number of valid operations. Now let's understand this with an example. Suppose the array is 1, 2, 3, 4 and k is 5. Can we find two numbers that add up to 5? Yes, 1 plus 4 equals 5. So that's one valid operation. Once we use those numbers, they are removed. The remaining numbers are 2 and 3. Again, their sum is 5. So that's another valid operation. Now the array becomes empty. No more pairs can be formed. So the answer is 2. Let's look at another example. The array is 3, 1, 3, 4, 3 and k is 6. The first pair is easy. 3 plus 3 equals 6. We remove both numbers. Now we're left with 1, 4, 3. Can we make another pair? 1 plus 4 is 5. 3 has no matching partner. So no more operations are possible. The answer is 1. These examples show something interesting. Whenever we pick a number, there is only one value that can pair with it. For example, if k is 6 and we pick 2, then the only number that can help us is 4. No other value matters. Keep that thought in mind. It'll become very useful later. But before we get there, let's think about the most straightforward solution. The simplest idea is straightforward. Take every number. Search the remaining array to see if there's another number that completes the sum. If we find one, we count one operation. Then we mark both numbers as used so they can't be selected again. After that, we continue searching until every element has been processed. This approach is simple. It's easy to understand. And it will produce the correct answer. So let's see how we'd write it. Let's convert that idea into code. First, we need a way to remember which numbers have already been used. One simple approach is to keep a Boolean array called used. Initially, every value is false. We also create a variable called operations. Initially, it's 0. Now we start with the first element. If that element has already been used, we simply skip it. Otherwise, we search the remaining array. Again, if a number has already been used, we ignore it. For every unused number, we check one condition. Does the current number plus this number equal k? If the answer is yes, we've found one valid pair. So we increment operations. Then we mark both numbers as used. And since each number can only belong to one pair, we immediately stop searching and move to the next element. After processing every element, we simply return operations. The algorithm is easy to understand. But let's verify it with a dry run. Let's use our first example. The array is 1, 2, 3, 4 and k is 5. Initially no number has been used. We start with 1. Now we search the remaining array. Does 1 plus 2 equal 5? No. Does 1 plus 3 equal 5? No. Does 1 plus 4 equal 5? Yes. We've found our first pair. So the operation count becomes 1. Now both 1 and 4 are marked as used. Next we move to 2. It's still unused. So we search again. Does 2 plus 3 equal 5? Yes, that's another valid pair. The operation count becomes 2. Now 2 and 3 are also marked as used. At this point, every element has already been used. So the algorithm finishes. The answer is 2. The solution works perfectly. But while doing this, did you notice something? For every number, we searched almost the entire remaining array just to find one matching value. That feels expensive. Maybe there's a faster way. Let's analyze the complexity. Suppose the array contains n elements. For every element, we may have to search almost the entire remaining array. That means we're comparing almost every pair of numbers. So the time complexity becomes O of n squared. Now let's talk about space. Apart from the Boolean array used, we don't create any large data structure. So the extra space complexity is O of n. The brute force solution works. But checking the remaining array again and again feels unnecessary. After all, we're only searching for one specific value. Can we somehow find that value instantly? That's exactly the question that leads us to the optimal solution. Let's think about what we're actually searching for. Suppose k is 10, and the current number is 3. When we used the brute force approach, we searched almost the entire array. But do we really care about every number? No. There's only one value that can help us. What number do we need to make the sum equal 10? It's 7, nothing else matters. Let's take another example. If the current number is 6, then what number are we looking for? We need 4. Again, there's only one possible answer. This is the important observation. For every number, we already know exactly what we're searching for. That value is called the complement. And we can calculate it using a very simple formula. Complement equals k minus current number. Now another question appears. Instead of searching the entire array, what if we could instantly know whether we've already seen that complement? If the complement already exists, we've found a valid pair. We can count one operation immediately. If the complement doesn't exist, then we simply remember the current number for future elements. That's where a HashMap helps us. Instead of searching, we perform a lookup. A lookup takes constant time, so every element can be processed only once. That's the entire idea behind the optimal solution. Instead of asking, "Can I find a partner?" we ask, "Have I already seen my partner?" That small change turns a quadratic solution into a linear one. Now let's see how we implement this idea. We'll process the array from left to right. For every number, we calculate its complement. Then we look inside the HashMap. If the complement already exists, that means we've found one complete pair. So we count one operation. Since that complement has now been used, we decrease its frequency inside the HashMap, or remove it completely if its frequency becomes 0. On the other hand, if the complement isn't available, then we can't form a pair yet. So we simply store the current number inside the HashMap. Then, we move to the next element. By the time we finish scanning the array, every possible pair has already been formed. Now let's write the code. Let's convert this idea into code. First, we create a HashMap. The key is the number. The value is how many times we've seen that number, but haven't used it yet. We also create a variable called operations. Initially, it's 0. Now we process every number in the array. For the current number, we calculate its complement. That's simply k minus current number. Now we check the HashMap. Have we already seen this complement? If yes, we've found one complete pair. So we increment operations. Since that complement has now been used, we reduce its frequency by 1. If its frequency becomes 0, we remove it from the HashMap. On the other hand, if the complement isn't present, then we can't form a pair yet. So we store the current number in the HashMap. If the number is already present, we simply increase its frequency. After processing every element, we return operations. That's the complete optimal solution. The code is actually quite short. The important part is understanding why the HashMap stores numbers waiting for their complements. Let's use the same example. The array is 1, 2, 3, 4 and k is 5. Initially, the HashMap is empty. Operations is 0. We start with 1. Its complement is 4. Is 4 already inside the HashMap? No. So we store 1. Now the HashMap contains 1. Next we read 2. Its complement is 3. Do we already have 3? No. So we store 2. Now the HashMap contains 1 and 2. Next, we read 3. Its complement is 2. This time the answer is yes. We've already seen 2. That means we've found one valid pair. Operations becomes 1. Since 2 has now been used, we remove it from the HashMap. Next, we read 4. Its complement is 1. Again, it's already inside the HashMap, so we've found another pair. Operations becomes 2. We remove 1 from the HashMap. Now we've processed every element. The HashMap is empty. And the answer is 2. Notice something interesting. We never searched the array. Every decision came from a single HashMap lookup. That's why this solution is much faster than brute force. Let's analyze the complexity. We process every element exactly once. For each element, we perform only a few HashMap operations. On average, those operations take constant time. So the total time complexity becomes O of n. Now let's talk about space. In the worst case, the HashMap may store every element. So the space complexity is O of n. Compared to the brute force solution, we've reduced the running time from O of n squared to O of n. That's a huge improvement. Let's quickly recap. We started with the brute force solution. For every number, we searched the remaining array to find its partner. The solution worked, but it required O of n squared time. Then we asked one important question. For any number, are we really searching for every value? No. We're searching for exactly one value, its complement. Once we started thinking in terms of complements, the HashMap became the perfect data structure. Instead of searching, we performed a quick lookup. That's the interview pattern to remember. Whenever a problem asks you to find pairs or values that satisfy a target, ask yourself this question. Can I calculate the value I'm looking for? If the answer is yes, there's a good chance a HashMap with complement lookup can lead you to the optimal solution. And that's how we solve LeetCode 1679. Max number of k, sum pairs. If you found this explanation helpful, make sure to like the video and subscribe to LeetCode. Thanks for watching. This is Huhu, signing off. Keep practicing. And I'll see you in the next one.